Hello and welcome to Algebra 2, Chapter 5.4, Complex Numbers. And I'm going to tell you now that this stuff is new. I would highly suggest you take notes, you write down examples, and if you have questions, go ahead and post them on the blog as you watch this so that we can see if we can get some of them addressed. So, good luck. Okay, so first we're going to talk about an imaginary number. And so the deal is, I can take the square root of 25, it's 5, or we've talked about it's plus or minus 5. But can I take the square root of negative 25? Right? And because if the definition of a square root is a number times itself, it's like 5 times 5 is 25, well, what times itself is negative 25? And the answer is nothing, because anything times itself is always going to be positive. But we had to have a way to solve equations that don't have real solutions. And so out came the imaginary number. Okay, so this is for an answer that's not a real number, and we use I for the imaginary number, and I equals the square root of negative 1. And so then I can take my square root of negative 25. I can use my product property and break this up into the square root of 25 times the square root of negative 1. Square root of 25 is 5. Square root of negative 1 is I. So it's 5I. So properties of the square root. So R needs to be a positive real number. And so here we go. Square root of negative R can be broken into I square root of R. Okay? And we also then need to know, and this one is going to be really important, that I squared equals negative 1. Okay? Because if I do the square root of negative 1 squared, remember a square root and a square cancel, and you're just going to get negative 1. So that is what I squared would be. So let's look at what that looks like when you're solving an equation. And these are going to be like the ones we did in 5.3, where we're going to solve by using the square root. So the first thing I want to do, if I'm looking at this and it has an x squared in it, I'm going to get the x squared by itself. Okay, so my next step is divide by 2. X squared equals negative 18. So your next step would be to square root both sides. And so remember, when you do that square root and you're solving for x, we have to add plus or minus. So at the moment, let's just write this as the square root of negative 18. But let's see what we can do to the square root of negative 18. So first of all, that's a negative 18. First of all, write it so you can read it. So this is going to be I square root of 18, because that is separating it into the square root of negative 1 and the square root of 18. But then 18 can be simplified, because remember, you always simplify radicals into 9 and 2. And so we're going to look at 3I square root of 2. And so that's what x equals, plus or minus 3I square root of 2. Make sure you follow that. And let's look at another one. Okay, so same deal. Remember, I am not going to distribute. I'm going to multiply. So I'm going to multiply by negative 2, both sides. Negative 2's cancel there. You're going to get x plus 1 squared equals negative 10. The next step then, square root both sides. So you're going to have x plus 1 equals plus or minus, okay? And let's go ahead, we're going to change this into the square root of negative 1 and the square root of 10. And the square root of 10 does not simplify, so this is I square root of 10. Subtract the 1 over, remember we're putting the 1 in the front. So this is negative 1 plus or minus I square root of 10. Okay, so we were just talking about I there, which is our imaginary number. So whenever you have an imaginary part, you actually have what's called a complex number. And a complex number is in the form a plus bi, where a is a real part and b I is the imaginary part. Now A can be 0, so if you just have 5I, that's a complex number because it would be the same as saying 0 plus 5I. But if B is 0, then you don't have an imaginary part and you just have a real number. So we're going to do several things with our imaginary numbers, and the first thing we're going to look at is graphing them. And this is called the complex plane, and notice on our two number lines we have our real number line, which is the horizontal number line, and we have our imaginary number line, which is the vertical number line. And so you're going to find the corresponding point to the real and the imaginary part. So we have four numbers to plot here. The first one, -4 minus I. So from the origin, you're going to go left 4. So you wouldn't necessarily draw it in, but you're going to come left 4, and you're going to go down 1, and there is your point. So you wouldn't really draw any of this in, that's just the path to get there. Okay? For 5, we're just going to graph real number at 5, so that's going to look like that at 5. And at 1 plus 3i, you're going to go over to 1 on your real and go up to 3i on your imaginary. So you need to look and make sure you know what the signs for those terms are. So the next thing we're going to look at is some operations with our complex numbers. And so to add and subtract them, really what you're doing is you're combining like terms. Remember, that is very important all the time. Whenever we're adding and subtract, combine like terms. So you're going to add and subtract the real parts because those are like terms, and you're going to add and subtract the imaginary parts because those are like terms. So we're going to write these in standard form. So standard form for a complex number, A plus BI. Okay, so if we look at this first example, remember just too, when you're adding binomials, if you're adding them, those parentheses don't mean anything. Okay, it's just saying, hey, you have this complex number and you're adding it to this complex number. And so let's add our like terms. We want our real number first. It's 2 plus 5i. That's your answer. Now if you are subtracting binomials, you want to distribute that negative sign. I would always distribute that negative sign. So there's the negative sign distributed. Now combine like terms. -1 plus 4i. Okay, so watch your signs. And this one I would distribute here and totally rewrite it first. 2i minus 3 minus I plus 2 minus 3i. We're going to collect the real parts first, so it looks like we have a -1. And then 2 minus 1 is 1, minus 3i is -2i. There we go for adding and subtracting. Next, we're going to look at multiplying, and remember you're going to distribute or FOIL. Okay, so we're going to multiply just like you always multiply polynomials. We do need to remember though that this, from that very first slide, I squared equals -1. Because now that we're multiplying, there's a great chance you're going to run into an I squared. So let's look at these three examples. You are going to distribute. So we're going to start out by writing it -3i minus I squared. And you are treating I exactly like a variable, except it's a variable that means a specific number. Okay, so after you get that, we're going to remember that I squared is -1. So this is -3i minus a -1. And then you're going to write them in standard form. So this is 1 minus 3i, because notice that 1 changed to positive. Okay, with the next one, we're going to FOIL. So for first, we get -12 minus 4i minus 18i minus 6i squared. We'll simplify here one at a time. Combining the middle terms, it's negative 22i minus 6i squared. And you're going to remember I squared is a negative 1. So that means this is negative 12 minus 22i minus 6 times negative 1. But 6 times negative 1 is a plus 6. And then let's add our real numbers, and they need to go in front. So this is a negative 6 minus 22i. Make sure you follow that. Okay, and the last one here, if you notice, this is a sum and product of a sum and a difference. So when we FOIL, you get 1, you get negative 2i plus 2i minus 4i squared. Well, your negative 2i, positive 2i cancel. I squared is a negative 1, so this is 1 minus 4 times negative 1, which is 1 plus 4, which is just 5. Okay, the next thing we're going to do is we're going to divide complex numbers. And so remember that you cannot have a square root on the bottom of a fraction. And so if I'm dividing by a complex number and I is my imaginary part of that, it's the square root of negative 1. So if you have an I on the bottom, that doesn't work. And so in 5.3 we talked about rationalizing the denominator. And so we actually multiplied by what's called the conjugate. And so now we're going to multiply by what's called the complex conjugate. And in case you've forgotten, a conjugate is the same numbers with the opposite sign in the middle. So if you look at 2x plus 3, the conjugate is 2x minus 3. And when I multiply these together, if I was to FOIL, my middle term cancels. So a complex conjugate is going to look like 2 plus 3i, and then the other one is going to be 2 minus 3i. And the deal is when you multiply those together, you no longer have an I, like that last problem on the previous slide. So if we're looking at 2 minus 7i divided by 1 plus I, there's not a whole lot of actual dividing going on here. We can't have an I in the bottom, and so you're going to multiply by the conjugate of the bottom, which is 1 minus I, and you do top and bottom. On the top then, we're going to FOIL because we have two binomials times each other. So this is going to be 2 minus 2i minus 7i plus 7i squared over 1. Now notice negative I plus I is going to cancel, minus I squared. So this is a negative 1, which makes this whole thing turn into a negative 7. So on the top we're going to have negative 5 minus 9i over. On the bottom this is a negative 1, which makes this turn into a plus 1. So it's over 2. So standard form would look like negative 5 halves minus 9i over 2. So that you can really see what your A and your B are. Okay, so let's do 3 more examples here just so we know that we have the multiplying down. So you're going to distribute. You're going to get 27i minus 3i squared. But what do we change I squared to? It's a negative 1, which means in this case this is going to be a plus 3. Standard form is going to be 3 plus 27i. Okay. On the next one, we're FOILing. You're going to get a negative 3 plus 6i plus 12i minus 24i squared. I squared, though, is negative 1, which makes this become a positive 24. So we're going to have 21 plus 18i, and make sure you get that. And on the last one, we're going to multiply by the complex conjugate, which is negative 1 plus 2i. You just change that middle term, that middle sign there. On the top, we're going to FOIL. You're looking at negative 3 plus 6i minus 11i plus 22i squared over positive 1, and then you're going to have a negative 2i and a positive 2i, which cancels, and a negative 4i squared. On top, this is a negative 1, which makes this be a negative 22. So it looks like we're going to have negative 25 minus 5i over, this is a negative 1, which makes this become a positive 4. So it looks like we got 5 on the bottom. Okay, we need to simplify because everything is divisible by 5, or if you look at it, if we separate this into two fractions, both of those can be reduced. This is going to become a 5, that's going to become a 1, negative 5 minus I. Okay, so the next thing we're going to do is we're going to find the absolute value of a complex number. So the first thing we're actually going to look at is the graph of 3 plus 4i. And so remember, we go out 3 on our real axis. We're going to go up 4i on our imaginary axis. That's going to put us about here. And we might want this distance. Okay, I'm going to talk about y on the next slide, but that distance can be important in some really cool things. And so how do I find that distance? Well, we can use the Pythagorean theorem actually, and we can do this distance squared and this distance squared, and we would take the square root of that. Okay, now, but if we have an I, we're probably going to be square rooting a negative, and so what we're going to do is we're going to call this the absolute value of z, or what you might actually refer to as c in most cases with the Pythagorean theorem. But all this is the Pythagorean theorem, and let's set it equal to z squared, that's been solved for z. So you square root both sides, okay, and this is what we get, the square root of a squared plus b squared. So let's actually find some absolute values, and then we're going to determine which is closest to the origin. So the first one here, so we're going to say z equals, or the absolute value of z equals the square root, and remember it's the square root of a squared plus b squared. So this is going to be negative 2 squared plus 5 squared, which is going to be 4 plus 25, which is the square root of 29. Okay. The next one, the absolute value here, a is 0 squared plus negative 6 squared, and so that's going to be the square root of 36, which is 6. And our last one here, absolute value of z equals square root of 5 squared plus negative 3 squared, which is the square root of 25 plus 9, which equals the square root of 34. Okay, so which one of these is closest to the origin is which one of these is the smallest number? So since, well, if we just look at them, if we compare the square root of 36, square root of 29, square root of 34, the smallest number, it's the square root of 29. Negative 2 plus 5i is closest to the origin. So why do I care about how close the number is to the origin? Well, there's been some really cool work on what are called Mandelbrot sets. And so this blue image here is a Mandelbrot set, and what this is, it is ordered pairs plotted on a complex plane, and they form these shapes. And so some equations or some numbers form Mandelbrot sets and others don't. And so if we're going to talk about an equation next, and in your equation, if it tends towards infinity, it does not form a Mandelbrot set. But if it tends to a certain number, and then there are different numbers, so if it tends to 1 or if it tends to 2, then it forms a Mandelbrot set, and you can actually plot these points. And so obviously then people color code. Maybe this layer is one color, the next layer is a different color, and you get these really cool images. And in fact, there's lots of study of these naturally occurring in nature. So, to determine if a complex number C belongs to a Mandelbrot set, you plug it into the following equation and work it out as follows. So you start by plugging f of z equals z squared plus c. So the first one you're actually going to find out, though, is f of 0, and it's going to always be 0. And you're going to actually find out the absolute value of each one of these. So you're going to do f of 0. You're going to find out what that equals, and then you're going to do f of that. So whatever that equals 0. So you can do f of 0, and then whatever that equals, you're going to do f of that, which is this one. You're going to do f of that, which is this one. And let's just do an example, and we will try to clarify that. Okay, so make sure you have this written down, and then let's do an example. So we're going to try to determine if negative 0.5i belongs to the Mandelbrot set. The first thing you need to do is replace the c in f of z with the c that it gives you. So f of z is now going to be z squared minus 1/2 I. And I'm just going to keep it as a 1/2. Feel free to keep it as a decimal. So then you need to find z sub 0, z sub 1, z sub 2, and maybe even more than that, and find their absolute values and determine then if they tend towards infinity or if they stay under a set number. So the first one we're going to find is z sub 0. And it says that z sub 0 equals 0, and it always does. So then we're going to find the absolute value of z sub 0, and we're going to remember that the absolute value of z equals the square root of a squared plus b squared. So this is just the square root of 0, which is 0. So then you're going to find z sub 1, and it says that z sub 1 is f of z sub 0. So this is going to be f of 0, which means you are evaluating your function up here for 0. So your z is going to become a 0. So this looks like 0 squared minus 1/2 I, which is just a negative 1/2 I. And then you're going to find the absolute value of z sub 1, which a is 0, so you're going to have negative 1/2 squared for your b, which turns out to be 1/2. So then we're going to find z sub 2. Well, z sub 2 is f of z sub 1, right up there. So we're going to have f of negative 1/2 I. So we're going to put in negative 1/2 I for our z, so this is negative 1/2 I squared minus 1/2 I, which is going to be a positive 1/4 I squared minus 1/2 I. And then remember that I squared is a negative 1, so this turns out to be a negative 1/4 minus 1/2 I. So then when I find my absolute value of z sub 2, this is going to be negative 1/4 squared plus 1/2 squared. And using the calculator, I get 0.559 for that. Okay, and let's do one more and see what we can tell. So let's do z sub 3, which is going to be f of negative 1/4 minus 1/2 I. Okay, because that is z sub 2. So putting that into my function, that is a negative 1/4 minus 1/2 I squared, because that all goes in for z, minus 1/2 I. We're going to need to FOIL this because that's what it means to square a binomial. So let me write it out. Okay, and then we're going to have to tack that one onto the end. So a fourth times a fourth is a 16th. And then we're going to have, see, a fourth times a half is an eighth. So plus 1/8 I plus 1/8 I plus 1/4 I squared minus 1/2 I. So remember, I squared is -1, so this turns into a -1/4. So we're going to have a 1/16 minus 1/4, which turns out to be a -3/16. And then for i's, we have 1/8 plus 1/8, and then minus 1/2, which is going to be a -1/4, so minus 1/4 I. So that is what z sub 3 is. Sorry, I switched colors there. So f of z, or the absolute value of z sub 3 is going to be the square root of -3/16 squared plus -1/4 squared. And I would just do that in my calculator. There. 1 second. Or hopefully you're trying this too. So I get 0.3125. And so, you know, you at least need to do 4 of these. It might be evident after 2 or 3 if this is going to go to infinity or not. But this one does not look like it's going to infinity. If I had some more room, I might try just one more. But we are going to say, yes, this is a member of the Mandelbrot set. And I'm going to do one more example like this so that hopefully it will clarify any questions. So we want to see if -3 is a member of the Mandelbrot set. So you're going to start out by writing f of z equals z squared minus 3. Okay, so that's our function we're using. So we're going to find z sub 0 first, which is always 0, and the absolute value of z sub 0 happens to be 0. Okay. So to write it out so you can see it, it's the square root of 0 squared, which is 0. So then we're going to find z sub 1, which is f of z sub 0, which is 0. So putting that into my function, this is 0 squared minus 3, which is -3. The absolute value of z sub 1 then is -3 squared. Make sure you put parentheses around your -3. B is 0, so there's no b, so this ends up being 3. So z sub 2 is f of z sub 1, which is f of -3. So this is -3 squared minus 3, which is 9 minus 3. Don't ask why I put another parenthesis there. Minus 3. Alright, so 9 minus 3 is 6. So then we're going to do z of 2 to find its absolute value, which is going to be 6 squared, which is 6. Okay. So then we're going to do z sub 3, which is f of 6, which is going to be 6 squared minus 3, which is 33. So then we're going to do the absolute value of z sub 3, which is going to be 33 squared, which is 33. Now, if I go higher, is this number going to continually get higher? Yes. Okay. So this next one here, 33 squared minus 3 is 1,086. So now when I do the absolute value of z sub 4, and I get 1,086 in here squared, so this is going to tend towards infinity. The higher I go, the bigger this number is going to get. So no, this is not a member of the Mandelbrot set. So sorry this was kind of lengthy, but it's lots of new stuff, so hopefully you took some good notes, and please let me know if you have questions. Have a good day.